Is it a bird?
No, it's a plane.
No, it's
it's the solar eclipse
just another
again.
solar eclipse. Yeah.
Oh, but they're still pretty cool.
Yeah, I guess. Well,
Einstein predicted the most cool theory, over 100 years ago, that we could use these things to measure general relativity, which I think is pretty cool.
that is pretty cool. And there's a pretty important solar eclipse coming up, actually, in just a couple weeks.
That's right. On July 2nd, we're going to have a total solar eclipse over the majority of South America.
So it's like the coast of South America and the Pacific. So those total solar eclipse cruises will be cashing in big time. I totally wish I was going to be on one. A little Mai Tai, a little solar eclipse.
We should plan one.
Yes, we digress.
These things are pretty common. So they're not, once in 100 years. But the reason this one is so cool is because it is the 100th year anniversary that some scientists proved that Einstein's theory of general relativity was indeed correct.
That's right.
And they did it just using a solar eclipse.
Just using an eclipse. No big deal.
That's pretty cool. So we're going to dive into what does that mean? How did they do it? And also some other cool fun facts on this week's episode of The Blast Off.
So I'm Dr. Rebecca Allen.
And I'm future Dr. Sara Webb.
So I think before we go into, using solar eclipses to prove this physics or that, we should talk just about the physics of what eclipses are, because there's different types of eclipses. We have solar eclipses and lunar eclipses.
That's right. So a solar eclipse, when I was little, I used to get these very confused. A solar eclipse is when the moon is in between the sun and us. And then a lunar eclipse is when we're in between the sun and the moon.
Yeah.
But it's
all about casting shadows.
It is, and it's when we're in a perfect line that they line up.
So
that makes sense.
So let's, for example, let's say there's a total lunar eclipse happening.
Mm-hmm.
So that means that, which I think are so cool. So they're both very cool, but I love the lunar eclipse because
you get that blood moon.
Yeah, the sun is shining behind Earth, that light's coming through our atmosphere, and so then the moon is cast in this shadow, but it's not just black, it's this reddish, very creepy yet beautiful hue.
Yeah.
And then when we have a total solar eclipse, now let's back up a second. So the moon is a teeny weeny little moon, especially when we compare, it with Earth, but then especially when we compare it with the sun.
It is a little speck of dust compared to the sun. But how does it block
the sun's light? Well, geometry. Yeah, we come back to geometry.
So the moon happens to be about 400,000 kilometers away from Earth, which is a huge distance, but compared to the thousands and hundreds of thousands of kilometers we are to the sun, when the moon passes in front of the sun, it happens to also be about 400,000 times smaller than the sun.
Yeah.
Which means that if we do some quick math, we end up seeing that it can cover the whole projection of the sun with its tiny little body.
So I have created this amazing illustration for you guys. So when you're looking at somebody and you just go, I'm squishing your head, I'm squishing your head. It's the exact same thing. So think about how far away you have to be able to squish that little noggin. And it's the same
of the size.
Yeah, it's the same principle with the solar eclipse. And so our little moon can actually block most of the light we get from the sun, but the alignment has to be just right. Because we think about everything being in this plane in the solar system, but the plane isn't, this paper thin line. It can vary a little bit, and the moon likes to bob and jig, and we bob and jig a little bit.
Some bob and jigs. It's all a whole bob jig fest out here.
It is.
But every once in a while, our bobs and our jigs are in a line, and we get these amazing eclipses. Yeah, which is pretty cool.
So the sun is bright.
I have noticed with my very white skin.
We're especially in Australia. It's like, I'm burning
constantly,
literally. And so if we want to see things which are very close to the sun, that's very, very hard because it's just saturated by the sun's light. Mm-hmm. However, when you have an eclipse, the moon is blocking out the majority of the sun's light except for its corona, which is its outer atmosphere, and it's a lot fainter. Mm-hmm. And so that's really cool because when there's an eclipse, scientists can actually study what's going on there.
Right, so we can see the stars that are up during the day during that time.
Yeah.
And this is where we come to Einstein's prediction of using these eclipses to test general relativity. So let's
break down.
So general relativity was Einstein's theory that described how space and time interact together. So he described that space-time would tell mass how to move and mass would tell space-time how to bend. So it's this beautiful relationship between mass and the fabric of space-time itself, which means that you've all seen those amazing, demonstrations where you put a bowling ball in the middle of a sheet and it bends. That literally happens in the universe. So we can consider our sun as a big-ass bowling ball. And then
all the little planets are just, within that well.
Within the well, that's right. And so if we can block out most of the light of the sun and look at a star that's really close to the sun, projection-wise on the sky,
it should be lensed.
It should be lensed, and it should move in its position to us. So that's very hard to do, especially back in 1919, back in the ye old days. So how did they do that?
Well, first of all, when we're talking about telescopes and you want to observe the sun, it's not like now where we have, CCDs and Nikon cameras. They had photographic plates.
So they would coat these things in this special fluid and hold it up or in front of a telescope, have the light projected. That's so cool.
Can you imagine if that was your job? Like, don't you move, Tim. Like, you gotta hold the plate.
And back in the cool old days, there used to be scientists at the tips of telescopes, so at the second mirror with photographic plates, pulling them in and out all night long. That would have been
God, it was like even that, or it's like not only holding the photographic plate, but these were made out of glass. So not only did Tim have to hold it, like very still, he better not drop it either.
And they got dropped a lot, especially when you're at the top of this big giant telescope.
Yeah.
Which is crazy.
So in 1916, that's when Einstein published his theory of general relativity. And, Einstein is a household name now. Everybody knows who Einstein is. But actually, back in the day when he was doing all this hard work, trying to be like, guys, look, I've got this really great idea. It's all relative. They were like, okay, sure.
Good for you.
And what I think is remarkable about this event is it's what really helped make Einstein a celebrity.
Yeah, and it solidified that his theory was not only a theory, but most likely still a theory.
It's still a theory.
It describes the universe better than we've ever had any.
Exactly. So it's understanding this large scale, how structures interact with space-time. Awesome job. Good on you. Very, very good math.
Good math.
But yeah, so again though, before we tell you exactly how they studied the eclipse and were able to use that to then tentatively support the theory of general relativity, because it was the first major, that's probably really right, but that was really hard to even get to that point.
Oh, it took years of getting to that point.
I just want to focus on solar eclipses a teeny weeny bit more, because last time we were talking about, ancient aliens, boo, some people like it, not judging.
It's just so interesting that people can legitimately believe that aliens traveled an insane amount of distance to come down to help us build a pyramid.
Look, it's the way you spin the facts.
I'm sorry, where are they? We have cancer and Donald Trump.
Yeah. please come back. Although maybe they're what gave us puppies and kitties. They were like, this is how you will cope. Have puppies and kitties. So thanks for that. Okay. But anyway, we're talking about these ancient civilizations and how they were able to, they were really the first astronomers because they found these patterns in the skies and they realized, oh, okay, well, when the sun is at this angle in the sky, then it's time to harvest our crops. Now we're getting more daylight. It's time to plant those crops, et cetera, et cetera.
Yeah, but based a lot of their spiritual ceremonies around them as well. So all different denominations based a lot of spiritual ceremonies around when
celestial events.
Yeah, and a big one was eclipses. Imagine back a couple thousand years ago, you're just sitting around, you're having a nice coffee in your hut, and all of a sudden the sky goes dark. What? Wouldn't you freak out? And a lot of them did. Poor little guys.
Yeah.
A lot of them freaked out and took it as a bad omen that something bad was going to happen.
Here's this, you know, constant in your life, the sun, very bright. And then all of a sudden it's not bright. And, you know, you're cast in this really weird in the middle of the day, or probably in the evening, you know, you have this eclipse. So for a lot of them, that meant freakouts. But then there were some really cool, you know, we'll call them cosmic coincidences if you read more into it. Yeah, that's you. Good for you. But let's say, like, for example, somebody's birthday.
Oh, this is a good one. So Muhammad, the prophet, there was a total solar eclipse around his birthday, which is pretty cool, because also if you go way back into some of the biblical writings about Jesus, there was actually there was writing saying that, you know, the sky went dark after he died, and a lot of historians actually take that to be, when these writings were written, is that the sky went dark because there was an eclipse, and we can, because our math is so good at our solar system, we can pinpoint when these happened. And so if that was right 2,000 years ago, that means that these writings are talking about the year about 39 BC, which is pretty cool.
That's amazing.
And so many other things have happened as well. And so Chinese emperors,
I was going to say, like, the Chinese and
they took the sky very, very seriously. So solar eclipses meant it was a warning for the emperor that, you know, you need
bad juju.
You need to watch what you're doing. And it's not an eclipse, but what is also funny, they took meteor showers and asteroids as also bad jujus. And so there was a couple of poor emperors that got exceptionally bad meteor showers in a couple of years running, and were, you know, punished almost by the people's judgment that, you know, the heavens,
you must be doing something wrong, if the heavens are angry at you.
But heaps of cool things happened. So there was also an eclipse. Hold on, what can you hearing? Oh yeah, so heaps of cool things happen around these eclipses. So another one is, you know, not thousands of years ago, but, you know, just a few hundred years ago, when King Henry the son died, there was a total total solar eclipse.
I wouldn't really call that cool.
I mean, not cool, but a cool coincidence that something so dark happened.
Interesting.
On a dark day.
Coincidence. But okay, so our history, a lot of our chronology, our spirituality, a lot of it is linked with celestial events, and total solar eclipses are super duper big events. But they're not rare, okay? All across written history, we see evidence of, you know, them being recorded. And so this is the idea, like, they're special, but they're not rare.
No, but where they happen on the earth changes.
That's right.
So often that you can imagine you've got one civilization that is, you know, pretty much barred from the outside world. It happens there once every, you know, 20, 30 years. That's a freak out moment.
Definitely a big deal. Yeah, I'm not trying to downplay it.
But now
I would totally freak out.
But now we know they happen quite often. And we can predict when they're going to happen. So there's going to be one in Australia in a few years, and I'm already wanting to be at Ezra.
Let's do it. We're going to do it. Yeah.
Which will be pretty cool.
Road trip. Hopefully it's not in the summer. But
watch it on TV.
Even if it is, we'll see it. And just remember, if you guys are watching a total solar eclipse, do not look at it. Do not take after President Trump and just look up into the sky, because it's very, very bad for your eyes.
Literally burn the back of your retina and, like, have a permanent circle in your retina.
And you're probably like, well, geez, I mean, the sun is up during the day and I glance at it and my eyes don't explode, so why is it so much more dangerous during eclipse?
And it's because you're focusing on that object, because during the day you're never going to look up and be like, sun's really nice.
I can focus on that burning sphere and get great detail.
And even though it doesn't look as bright because you're only seeing the corona, it's still really, really bright.
Loads of photons, okay? These little receptors, these guys are sensitive.
They're not made
Protect your eyes. Protect your eyes. But we can use scientific scientific instruments to look at the sun and take data. And so back in the day, in 1919, we had the photographic plates. And so essentially what they were trying to do is to get what we call exposures. So they were taking pictures, and they were trying to get the light of the stars. And then what they wanted to do is compare those exposures. And so what you'd have to do is you have to observe the star field when it wasn't by the star. So maybe like 6 months earlier or after. So this is what the star field looks like. And then you have the sun in front of the star field. And then you're taking that image during the eclipse. And what you're looking for is basically the sun and its big old mass bending space-time. And you know what? Light is in space-time, so light gets bent too. And so it acts as a lens. And so what you're looking for is that angle that it's been bent.
Right, so you should see stars either side and up and down, just bending a little bit towards the sun. And by like
I was going to say this effect is so teeny.
So tiny.
Which is very hard and to measure, and which is why, even though it was incredible, you know, it's like Einstein was probably right, because that data, you know, wasn't the best quality.
No, so they took, I think, maybe 4 or 5 different exposures. This one team led by, how do you say his name?
Eddington.
Sir
Arthur Eddington.
I keep calling him Eddingman. But Eddington was an interesting character in himself.
Yeah.
He actually, the reason he was one of the scientists on this, apart from being a professor in astronomy, was he didn't want to get drafted into the war.
Can't blame him.
Can't blame him, but they used this total solar eclipse to actually get a heap of scientists out of going to the war, which is...
Yeah. And I just want to say, you know, we look back and there's all these prominent names in physics, and, you know, people are people. They're all not always the best people, but you can gosh darn guarantee that they weren't the sole person that made the discovery, that there were other people that supported them.
Especially students.
And especially lesser known, maybe Indian astronomers who were right about what black holes were, but I digress. So.
Because Charskinger, I always have trouble saying his name.
Chandrasekhar?
Chandrasekhar. Charskinger. I can type it perfectly. Chandrasekhar was Edmonton's student, and he was a boy genius. We digress a little bit, but he deserved it.
At 21, he basically figured out what singularities were.
Yeah, he figured out that Charskinger mass limit, that if you're a neutron star and all of a sudden you reach this mass limit, the Pauli exclusion principle comes into play, and all of these neutrons collapse in on each other, which is just mind-boggling. And until then, we had no idea.
No, and we will delve into, philosophically, black holes in a different episode. So before we wrap up, you know, we've gone through several different kind of concepts today. We've explained to you what eclipses are, kind of the science that we can get from looking at a solar eclipse, and even their significance throughout human history.
Even though they are just cosmic coincidences.
They are just cosmic coincidences.
But they're still cool nonetheless.
Absolutely.
And so with this one, they're going to try retest general relativity again in July, even though they don't need to, because now we're in the era of the most amazing gravitational wave experiment.
That's right. So first of all, you got to love a good throwback, and the fact that, you know, technology has come so far since 100 years ago when they were using photographic plates. And so now we do have these things like CCDs, but it is still very hard, even with modern technology, to try to recreate the experiment and then measure those results. It takes a lot of time and coordination. But I want to, you know, jump off what Sarah just said. So that's great. We could look at this and we could try to look for the bending of light around our sun. But now we also have detections that, you know, don't depend on light, that can tell us about how space-time is being bent.
Which is pretty damn cool.
It's amazing.
Part of Einstein's general relativity was not only that light would bend around
New word.
massive gravitational wells, grassive wells we'll call them from now on. Not that only light would bend around them, but that massive interactions between really heavy stars or black holes would create gravitational waves. Or in fact, anything moving through space technically creates a gravitational wave, but we would be able to detect these massive gravitational waves from colliding black holes and stars.
It was another one of Einstein's predictions, but unlike the eclipse, he, you know, basically thought that, you know, we were talking about last episode, the percentage of, you know, perhaps life being able to detect us. It's even smaller than that. He wasn't even like, oh yeah, it's a 0.1% chance. He's like, it's a 0% chance, essentially.
Because of the technology, especially back in the 1920s when Einstein was considering, how could we possibly detect these gravitational waves, the technology was so far advanced, and we're only just now, 115 years later from when he first started to conceptualize the idea, able to do it. And we do it with facilities called LIGO. So we have advanced LIGO now, and then we also have Virgo, which is pretty cool. And they're these massive interferometers. What is it? A Wilkinson's interferometer?
Yeah, so it's a type of no, I can't say it.
Say it again.
It's lasers.
Yeah. So they're these massive laser interferometers, and so you have two laser arms. So
they have to be perpendicular.
All of these are lasers, and they're spread distances apart. So from my head to my fingertips is about 3 kilometers, and at the end of that there's a mirror, and it bounces this laser back and forth, and it happens on this perpendicular plane. And if a gravitational wave comes through Earth and stretches one of my arms a little bit, here when we're detecting the light coming back in, because they should be in phase if they're...
And so then cancelling each other out.
Yeah, which will put a pretty graphic of what in phase and out of phase looks like. But if one of my arms stretches a little bit because a gravitational wave has pushed me together, we see that happen in the detectors. And that's what we call these little chirps, or the in-spiral chirps, which is pretty cool.
And, like we said, we're going to go into black holes and compact objects in another episode. So we'll explain this a bit more, because that's the idea is, Einstein really was before his time, because he was able to take his creative, artistic analysis and take these concepts, which really are, especially to him, they were pure mathematics back then. Yeah. And so now we're actually able to, see them through these detections of gravitational waves, which, aren't light. Everything we know about the universe really up until this point has been through light.
Yeah, everything we know is because of the electromagnetic spectrum, but this is the first time that we're able to look at things without needing photons to tell us what happened, which is pretty cool. Yeah. But we'll dive into a lot of all of that in many different episodes on Einstein, on gravitational waves.
There's so much more.
And it's so good, and all of it is so juicy with science facts. Yeah. But for now, I think we look forward to the eclipse, and if you guys are in South America or the very south of the United States, you should definitely look out for it, but remember to wear glasses.
Absolutely.
Don't do a President Trump.
Don't just look up at the sun. Don't just look up at the sun, period. Appreciate its presence without staring at it. Nobody likes to be stared at, right? So give the sun its space.
Privacy.
But yes, so please enjoy the eclipse responsibly, and we'll be back. Thanks. This has been
The Blast Off.